the diameter of the nucleus, is basically 10 to the minus 15 meters, whereas the whole spherical diameter of the atom is 10 to the minus 10 meters. There is a big difference in those numbers. Have half a neutron or half a proton. The atomic number is the smaller number associated with an element. This is the number of protons. You will frequently see the atomic number with the symbol Z and the mass number with the symbol A. Now the mass number is the total number of protons and neutrons, which is why having a mass number of 35.5 or whatever decimal is a bit strange. But it can be a decimal because it is an average number of the naturally occurring isotopes. We can have isotopes of an element or different versions of an element. Here we have carbon 12 and carbon 14. They will have the same atomic number, 6. They will have 6 protons, but they will have a different mass number, 12 and 14. This is due to a change in the number of neutrons. We calculate the mass from this by looking at the number of protons plus the number of neutrons. And an increase in neutrons from a 6 to 8 will give us an increase in mass. They will have the same electronic structure, the same number and arrangements of electrons, so they will have the same chemical properties. But their different masses means they might have different physical properties. Here we have a crude diagram of a time-of-flight mass spectrometer. Your unknown sample is mixed with a polar solvent and inserted under high pressure.
Okay, so it has the same electronic structure, which means that they have the same chemical properties, but they have different physical properties due to different mass because of the neutrons. So isotopes, they have the same number of protons. Same number of protons, different number of neutrons. Okay, now we're on the time of flight mass spec.
Sure. Ionization will occur by electrons or by spraying. Acceleration will occur by electric field with smaller
ionization. Ionization, there's two ways: electrospray and electron impact. Then there's acceleration, which is where ions are accelerated by an electric field. The smaller ions go quicker than the bigger ones, faster, but they all have the constant kinetic energy.
Ions going faster. And here we can use the equation for kinetic energy. Half times mass times velocity squared. The speed would depend on the mass and the charge, with heavy things going slower. And the detector will see the ions creating a small charge. This is what we will get as the results. And they can be used to calculate relative mass. The NZ is the mass-charge ratio, and all of these numbers are positive. The mass number that we see on the periodic table is an average of all of the naturally occurring isotopes of an element. We can use the mass spec to work this out. Here we see that 20% of the naturally occurring boron has a mass of 10, and 80% of the naturally occurring boron has a mass of 11. So we can do 20 times 10 plus 80, the percentage, times 11, the mass, divided by 100, which is the total of the percentage. This will give us 10.8 as the relative atomic mass for boron, and this is the number that you will see written on the periodic table.
Okay, that's good.
Unfortunately, the structure we have, the picture that you're used to drawing of an atom, is fake. We need to look at the cells, the subshells, and the orbitals. We can look at the periodic table and we can categorize things as D block, S block, F block, or P block, all based on the cells, subshells, and orbitals. And we can draw them like this. So, for example, if we look at calcium, it has 20 electrons. So we are going to start filling from the bottom. Each needs to be filled singly, each electron, and within each box they must have opposite spins. 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10,
opposite spins.
11, 12,
Is it something to do
13,
with repulsion?
14, 15, 16, 17, 18, 19, 20. That is the electronic structure of calcium, but we can write it out a bit neater. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Here we have a shell. This is a subshell, and this is an orbital. They are very easy to get these confused if you're not 100% clear on what is what. The shapes of the atomic orbitals can be looked at as S, P, F, D.
S is just a circle.
They can be spheres, they can be dumbbells, and all are present at once. We start with 1s and then 2s and 3 2p orbitals. Each orbital can hold 2 electrons. So the total number of electrons in the first shell is 2. In the second shell, it is 2 plus 6, giving us 8.
What's 6?
The shorthand way of...
Hold on. If each orbital can hold 2, 1s2 is 2. But then 2s, because shouldn't it be 4? Wait, 2s... Oh wait, no, 2p. 6, but because it can hold 6, it has 3 subshells. Okay, I think my brain just broke in halfway. Okay, I kind of do understand.
Writing this literally looks at the shells and the orbitals and the number of electrons. So argon's 18 electrons are 1s2, 2s2, 2p6, 3s2, 3p6.
So it's full.
The shorthand for that would be argon in square brackets. Calcium has 20 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but that's a bit of a mouthful. So we can say argon, which covers that first bit there, 4s2, because it's got the noble gas arrangement.
So that's good.
Ions are atoms that have lost or gained electrons.
Okay.
For example, here we see the electronic configuration for calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now you can either remember this, which you can do for the group 1 and group 2 as +1 and +2, or you can work it out. Group 1 will form +1 ions, Group 2 will form +2 ions. The transition metals have a variable oxidation state. Group 7 will form -1 ions. Group 6 will form -2 ions. But they are all aiming for a noble gas configuration. So here we have calcium's electronic structure. It is here. It has these electrons in the 4s2.
So it'll be fine
and to get to noble gas configuration, it is going to lose those electrons,
Okay.
one at a time. So it has now formed a +1 ion. Losing another one will give us a +2 ion. And we can change the way we write the electronic structure to reflect that. These are some really important definitions to learn and to make sure you understand properly. The first ionization energy
Oh no, I know that.
is the energy that is required for the removal
So it's the energy
of
required.
one
yeah.
electron from
For the
each
removal.
atom within 1 mole of
Gases.
atoms in a gaseous form
Yeah.
to make 1 mole
Why is it so long?
of gaseous +1 ions. Hydrogen, and using our state symbols gas,
H
will be
plus
turned into
gas.
hydrogen
plus
ion gas +1 electron. Sodium, gaseous form, it is really important to
first
get these right,
ionization is
will
the
be
energy
turned into
required
sodium
for the
plus
removal
in
of
gas
one
form
electron
+1
from
electron.
each atom.
The second ionization energy
Is the
is the
second
energy
ion
that is required for
the
the removal
electron? No?
of 1 electron from each ion within 1 mole of +1 ions in a gaseous form to make 1 mole
Why is this
of
one so
gaseous
much harder?
+2 ions. Our equations, and
It'll
again,
be
it is important to get the
He
state symbols correct
makes
here.
He
Gaseous.
plus 2
Helium
plus
plus will go to
E.
helium 2 plus 1 electron. Sodium plus will go to sodium 2 plus in a gaseous form +1 electron.
Okay, this I understand. I understand the equation.
There are a number of factors that affect ionization energy.
Oh, I know.
The atomic radius, where the larger the distance between the nucleus and the outer electrons,
Then it'll be easier for
the
the
less the attraction will be.
So it's easier to get the electron.
Electron shielding or electron repulsion. Electrons are all negative.
All negatively
And the
charged.
inner ones, the inner electrons, repel the outer electrons,
Okay.
reducing the attraction.
So they reduce
Nuclear charge. The more protons in the nucleus,
the more protons in
the
the nucleus.
greater the attraction between it
And
the outer electrons.
Okay.
If we look at trends in successive ionization energies, we can see some patterns.
It increases.
The first 7 electrons on an outer shell follow a different pattern to the 2 electrons on the inner shell. We can see a big jump here between
Okay, so that means
electrons
it's
7
moving on to
and
the
electrons
other
8.
group, I think.
There is a big jump
in
in
ionization
ionization
energy, which means it's increased. So
it is always going to get
it's
harder to remove electrons. And as electrons are removed, the repulsion between the remaining ones is less.
Okay, so then it... How does it...
When we are looking at trends in ionization energies, we will see that there is an increase across periods. There is a sharp drop in the first ionization energy between the end of one period and the beginning of the next. And these 2 bits of data give us the evidence for shells. Ionization energy can provide evidence for electron structure. If we look at our graph here, we have increasing atomic number. Here are the groups, and this is the ionization energy. There is a small drop in ionization energy between groups 2 and 3. For example, beryllium to boron and magnesium to aluminium. This drop can be used as evidence for electron configuration. If we look at beryllium and boron, the 5th electron is the first one in the 2 pair. Because a new subshell has been started, the fifth electron is evidence for electron configuration.